Uh, Hello, everybody. I hope you can hear me well. Thank you very much for the opportunity to talk to you. I'm really happy to see all my NOIR Lab coworkers and colleagues there. I wish I could be there with you, but well, maybe next time. So I'm also really glad that my talk is just right after Kim's, because I knew that she would give such a great introduction to low metallicity stars and would get everybody really excited about them. So my job now is, I think, easier, right? And I cannot state how happy I am with the results from GHOST. You know, seeing HD 222925 there, it's really amazing, right? I could go on and on just by that, but I won't. So the reason I'm here is I want to talk about two things. And the reason my background here has clouds is that I want to talk about bad weather, right? And this is the only picture I could find on the NOIR Lab website with Gemini and clouds, actually. So that's why it's here. And the reason I want to talk about this, I realized that I've been using poor weather proposals on Gemini for actually 25 semesters now. So there has been thousands and thousands of stars observed and a lot of good science done with bad weather. And I just wanted to show you here, not only talk about a little bit about the bad weather, but also share a very interesting result that we found next year. It's a very chemically peculiar star that we found in the halo of the Milky Way. So since Kim did the introduction for me, I'll just go really fast through my intro slides. And the one thing I wanted to show you, and assuming that I have control, let's see, let me try this. Oh, okay, good. So then you see my periodic table here. So this is, well, my science question. This is why I do science, is just to understand how the universe can go from hydrogen and helium only, all the way to all the elements we see in the surface of the sun and the surface of these low metallicity stars, right? We know all the physics, or most of the physics behind this, stellar evolution, some sort of burning stages, explosive stages, but then we want to know a little bit more about the specific astrophysical sites, fractions, mass distribution of progenitor populations, and so on and so forth. So that's why we observe those really low metallicity stars, and we call this stellar archaeology or galactic archaeology, or depending on your inclinations, you can say near field cosmology, or also known as the universe as z equals 0, right? And this, again, this is the same timeline you just saw. Those really massive stars were born, metal-free, exploded, polluted the interstellar medium with metals. Then we formed the second generation low mass stars, and those would live for, well, 13 billion years, and we would see them today in the halo of the Milky Way. That's how the story goes, right? So if we observe them today, we can just trace back the progenitor population and say, hey, in order to give this abundance that we see today, maybe I needed a first star with such mass and such distribution of parameters. And if you want to do that, of course, you need high resolution spectroscopy, as we saw for GHOST, for example, right? And here on the right-hand side, I'm just showing two spectra of a solar type star and of an ultra metal poor star, just so you have an idea of the amount of lines you can see in both of them. So for the ultra metal poor, these are really hard to find. I think the community in its entirety, I think, found 36 of those so far with high resolution spectroscopy. So they're really hard to find. I think it's about maybe 1 per 100 square degrees of the night sky. Again, so these are really rare. So what you do is you increase your chances of finding them by doing smart pre-selections, right? You can do Gaia, you can do moderate resolution spectroscopy, or you can do narrowband photometry, just like the pristine survey that Kim just mentioned. Another effort to do narrowband photometry is this project called Southern Photometric Local Universe Survey, right? It's a 0.8 robotic telescope sitting in a mountain or in Chile, our own Cerro Tololo. Here you can see on the bottom of the image. This is what we call the mushroom farms at Cerro Tololo. So the S+ telescope is the one on the left-hand side of the picture. So this is a 2 square degree field of view, just scanning the southern sky, 8,500 square degrees. I think what you see in the top right is just the current footprint, which is about 4,000 square degrees. And what's special about the survey is that they have 12 filters. So they have 7 narrowband and 5 broadband. And this is what you can see here on the left side. Some of those narrowbands, they're really well positioned. Calcium lines, hydrogen lines, magnesium triplet, calcium triplet. So you can get not only your stellar atmospheric parameters, but you can also get selected chemical abundances. And you can get your temperatures also from the broadband photometry, right? On the right-hand side, I'm just putting just two animations of an extended object and on a stellar field, right? Because if you have those 12 filters, this is pretty much a low resolution IFU, right? So for each pixel of those images, you have those 12 pieces of information in terms of the spectral energy distribution. So we use those in order to pick interesting stars for spectroscopic follow-up. So for the calcium filter, on the left-hand side, you see how different metallicities behave for a given temperature. So these are synthetic spectra, same temperature, just varying metallicities on the top. And on the bottom, you see how those changes in metallicity reflect on the actual integrated flux on that band. So in principle, you can distinguish very well between solar type stars, metallicities -1, -2, -3, and even a little bit lower than -3, right? And on the right-hand side, what you see on the top is just the same thing for this S+ filter, this Havalambre filter system on the top. And on the bottom, this is just an example of the SkyMapper little v filter, which is a little bit some sort of wider and slightly bluer. You can still pick out a lot of metallicity information, but the narrower one, which is essentially the same as the pristine one, it's very, very powerful in that sense. So what we did for this particular work is, okay, so we have those 12 magnitudes. So can we find a color space where we could isolate low metallicity stars and increase our chances of finding them? And this is what you see here. So on the left-hand side is just a color diagram. So the colors are a little bit weird, but again, color diagram. And the blue box that you see on the zoom on the right-hand side is just a region of that space, but then color-coded by metallicity. You see, as the points go from blue to black, these are metallicities decreasing. So as you can see, if you go to the bottom left corner of that image, if you select stars over there, chances are most of those will be low metallicity. So that's what we did. We just picked 500 stars from that bunch and say, let's do spectroscopic follow-up and see what happens, right? And this is where Gemini poor weather programs come into place, right? Because these stars are fairly bright. So let's talk about, well, the good, the bad, and the poor weather. So here I have two time lapses from our Gemini South all-sky camera, and I want you to try to guess which of those two nights that I actually got data for my Band 4 program. This is just a 30-second video. Just, again, enjoy the visuals. And again, both nights, telescope is open for most of the night. And then at some point on the left-hand side, you see that, again, clouds, bright, the moon is up. So this is where I got data, right? So this is the sweet spot for your poor weather program. Again, you can still do a lot of science in those conditions. And here, you just see a snapshot of those two nights. On the left-hand side, this is an actual snapshot of the last spectrum I got from my, the 22A poor weather program. So this was June 20th. So this is the actual, the telescope is open, you can see. And on the top left, you can see the GMOS spectrum that I got for a particular object. We have that problem with AMP number 5 on GMOS, but that doesn't prevent us to do great science with that data, right? So this was the last one we got for this particular project. So looking at all of the data for those Band 4 programs for this particular paper, this is what 91 hours of Band 4 time at Gemini give you, right? So here we have 138 stars, and out of those 91 hours of awarded time, we have almost 46 hours on target, which to me, since this is a poor weather program, and as you can see in the title of the slide, the conditions are, well, whatever, right? If you can open the telescope and point somewhere, again, you can give me that data because I will use it, right? And this is the result. We have 138 stars, and all of them, you can see here, the calcium lines, Balmer lines, carbon G-band, magnesium triplet, everything. You can get reliable parameters for all of those stars taken under poor weather conditions. So we used those 138 stars, and then we went to our friends on Cerro Tololo with the Blanco telescope and the Cosmos spectrograph, and we observed another 384. So we have a combined sample of 522. And this is what you see here on the top left. This is just the footprint of the observations. The bottom shows just the magnitude distribution for 8 of those 12 filters. And hopefully the image is not too small for you to see, but then on the right-hand side, I'm showing 50 spectra on the left side taken with the Blanco and the Cosmos spectrograph, and on the right-hand side, it's Gemini GMOS. And as you can see, those are really, similar. Gemini data taken under poor weather conditions is really amazing to do that type of science. And again, all of those stars over here reduced with the Dragons pipeline. So thanks, Kathleen and the team, for sharing the development version with me. All of those reduced using Dragons. So what we did was we took those 500 stars, calculated the metallicities, and this is what we get. The top histogram here shows our success rate in finding stars with metallicities below -2, because these are the most interesting ones that we want to find. And our success rate is about 83% of all of those have metallicities below -2, which is pretty good, right? And if you look here on the right-hand side, the color diagram, we picked one star here that had a metallicity from GMOS at about -4, and we did reobserve that star with Mike on the Magellan telescope. And this is what you have, right? On the top here, you have your 12 points, so your really low resolution narrowband photometry type. Then you have your GMOS data. Again, 5 minutes of bad weather give you this. And then you have the Magellan high resolution. And again, I put a ghost emoji here. I don't know if you can see it. And that's an opportunity for ghosts. Absolutely, we could observe that star with ghosts. And this star turned out to be super, super interesting, right? You have high resolution data. You can do spectrosynthesis. Again, this is carbon, this is lithium, and this is strontium. So we can measure all of those elements in that star. And we can measure, a bunch of, lighter elements. But what's interesting about this is that this was the lowest carbon ever measured for a low metallicity star in the Milky Way, right? And you can see here the dot over here, the lowest carbon ever. And what that tells us about, for example, the makeup of the first stars is that, well, you need to find a progenitor population that would give such a low carbon abundance in the interstellar medium and in the gas cloud that actually formed that star. And we can do that here, and you see on the bottom that the points are the observed abundances, and the lines are all some sort of theoretical models for a zero metallicity faint supernova explosion and the chemical yields from that. So we can compare that and say, well, the most probable progenitor population has a 29.5 solar masses metal-free. And this is, again, an unexpected result, again, coming from Benford. I don't think I can state that enough, is that with 5 minutes of GMOS time under poor weather conditions, we can actually put a constraint on the IMF of the first stars to be born in the universe. And this is not an overstatement, right, by any measure. We can do that, right? And this is how amazing this is. And we can continue doing that now with GHOST. That's why I think people are so, I know at least 20 people who would apply for GHOST time tomorrow if available. And my second to last slide is just to summarize all of this work, is that this is really the power in numbers, right? We have this S+, this really tiny robotic telescope that observed 20 million objects. Then by doing smart selections, we got down to 500, observed 138 with Gemini under poor weather conditions, not the picture that we see here. Then got the most interesting one out of those, put on Magellan, and hopefully in the future with GHOST, the emoji is here again. And then we find one of those very chemically peculiar and pristine stars, right? And this star actually made, the rounds in the press, and it got some interesting things to talk about just because it was such a low carbon abundance. And then I actually have my summary slide. I'll just stop talking. I'll leave you here with another picture with clouds, because I think one of the takeaways is that, well, the poor weather shouldn't be seen as weather loss, in my humble opinion. It should be seen as an opportunity to innovate, as an opportunity to try different things and try maybe things that you wouldn't otherwise try in a regular tack. So I'm really happy to talk to anybody about those poor weather opportunities. And again, I think the future is really bright for GHOST. Well, bright and faint, depending on what you have, right? But the future is great for people who are using GHOST, and I'm really happy to be just part of it now. I think that this is really amazing. I'll leave you with my conclusions. I'm really happy, to give this presentation. Thank you again for your time, and I'm happy to take any questions if you have them. Thank you.
Great. Yeah. Thanks so much, Vinny. What can I say? Take that, radio astronomers. That's some super cool work and really great featuring how you can really do some great science in cloudy weather. First question, Denise.
Oh, thanks. It was really great talk, Vinny. I have a question because you said that in your color color diagram, you see a number of there you selected the metal poor stars, and they said you have a chance that they will turn to be really low metallicity stars. So what was the fraction of those you selected that tended to be really the kind of object you're looking for?
Okay, so I think you're talking about this, and oi Denise, by the way, well, good to see you there. Yeah, so the fractions, well, as we saw, is about 80% for metallicities below -2, which is, and for metallicities below -3, I think it's about 17 to 20%, which is great, right? Because usually, really if you want to randomly find a star at -4, you actually have to observe 1 million of them and find one. So in this case, we observed 500 and some 2. So yeah, thank you.
Yeah, this is perfect because in general, what we expected with this kind of diagram is that perhaps we'll not find that many objects. So this is a really good one, and then the way you follow it, that's perfect. Thanks.
Thank you.
Time for another question, Zach.
Hey, Vinny, I had a question about your magnitude distribution, because I may have missed it, but I was just wondering, like, what ranges were your targets in terms of like V magnitude or the band you were looking at?
Oh yeah, okay, maybe it's this one. Yes, so we had things ranging from 12.5, 13 G magnitudes all the way to 17.5. So Gemini got the really faint end of that distribution. So anything G greater than 16.5, that was GMOS, and these were all 20 minutes, half an hour on a really bad day, but 20 minutes gives you a really nice spectrum already. The ones you see here.
All right, yeah, this looks great.
Great, let's thank Vinny again and move on to